Hi one and all. So in this video I'm going to explain how to simulate and verify the working of ring counter, and similarly we shall see how to simulate and verify the working of Johnson counter using the design suite called Xilinx. Alright. So first we shall discuss about ring counter at a high level, and then we shall see how to write the VHDL code for ring counter. Then we shall discuss about Johnson counter at a high level. Then we shall see how to write the VHDL code for Johnson counter. Finally, we shall end the session by practically implementing ring counter and then Johnson counter by using the design suite called Xilinx. Clear? So I already have mentioned in the previous class videos saying that whenever you come across counter, make sure that flip-flop will come into picture. Means usually we have to use flip-flops to design the counters. So here we are going to use 3 flip-flops because here we are assuming that counter is dealing with 3 bits. So and let us assume the ring counter initially has stored 100 as an initial value. So one flip-flop for this bit and another flip-flop for second bit and another flip-flop for the last bit. Hence I said we shall assume that the ring counter here are using 3 bits. Clear? So and assume that the ring counter initially it has a value 100. The decimal equivalent of this 100 is nothing but 4. I mean now the counter is in the state called 4. Clear? And assume, as I said, this is the initial state of the ring counter, right? And when we apply the clock, I mean at this state, if we apply the clock, what would be the output of ring counter? It is nothing but so how it will generate that output is, first it will take the bit present in the last place, okay, and then it will place it in the first place here. Then it will shift the bit present in this place towards right side, and again similarly it will place the bit present in this place to the right side. So 010, the decimal equivalent of 010 is 2. Means if the ring counter is in the initial state 4 and after applying the clock it will enter into the state called 2, right? Again if you apply the clock at this state, okay, then what would be the output of the ring counter? How it will generate the output value? So first it will fetch the bit present in this place and it will put it in the first place. Then it will shift the bit present in this place towards right side. Then again it will shift the bit present in this place towards right side. So 001, it is in binary, the decimal equivalent of 001 is 1. It means if the ring counter is in second state and if you apply the clock, then it will reach to the state called 1. Clear? Again if you apply the clock, what happens? Again if you apply the clock, same, it will take the bit present in this place, it will put it in the first place, and it will shift the bit present in this place towards right side, and again similarly it will shift the bit present in this state towards right side. Means again it will go to the state number 4. Clear? So this is how the ring counter will work. Now we shall see how to write the VHDL code for this behavior, to achieve this behavior. Clear? So we understood theoretically or at a high level how ring counter will work. So then before writing the actual logic, first you have to go through the port description. Okay, C stands for clock here, I mean this clock input, and R stands for reset. I have already told you in the previous videos what is the job of reset pin. Exactly, even here we are using reset to reset the counter, with some initial value. Clear? Okay, then what is this Q? Q is actually a counter and the mode should be set to in and out, because I already told you how to decide this. Correct? Once again I will repeat here why the Q should be in and out, and it should be a vector of dimension 2 down to 0. Why it is 2 down to 0? Because we are using 3 flip-flops here in this case. See here, 1 flip-flop for this, 1 flip-flop for this, 1 flip-flop for this. Clear? Okay. Now we shall go through the actual logic. I have already told you that whenever you heard the word called flip-flop, and if your requirement is to write the VHDL code for flip-flop, then make sure that you have used a construct called process. Clear? Okay, and here we need to pass clock and reset as the parameters, and here you are checking that whether reset has been applied. If reset has been applied, then initialize the counter Q with the value 100, which is nothing but this 4, decimal value 4, means initially the counter will be in the 4th state. Clear? Okay, and if you apply the clock, else if clock is equal to 1 means if you apply the clock, then counter should go to this state. Okay, can you see here Q is also present towards right side of the assignment operator, and Q is also present towards left side of the operator, and hence the mode should be in and out. Means you are using Q for both reading as well as for writing purpose. Clear with this? Okay, now we shall understand how actually to write this particular statement here. Clear? See, look at here. I have already told you that vectors is similar to arrays in C or in C++ or in Java, right? And you know that array indexing will start with 0, 1, 2, etc. like this. I mean, if the array has two values, say that 10 and 20, so first element will be stored in the 0th place, next element will be stored in the 1th place, etc. and so on. Means indexing will start from left to right, but in VHDL, indexing will start from right to left. Means this will be the first bit, second bit 1, and this will be the last bit 0. Means from here to here. This is very, very important. And with this idea, just observe here, and if let us assume this is our present value of the counter, what we are doing when we apply the clock to the counter, we are taking the bit present in the 0th place, right? We are taking the bit present in the 0th place and we are putting in the first place, right? Correct? That's what here you are doing here. First take the bit present in the 0th place and put it in the first place. And this ampersand operator in VHDL is acting like a concatenation operator. Have you heard the word called string concatenation? What string concatenation will do? It will just append the second string to the first string, right? Exactly same here. It will append the bits present in this place. I will tell you what are those bits to this bit. Okay, if you have if you have no idea about string concatenation, I will tell you. See, let us assume we have a string called S1 with the value hello. Let us assume we have one more string called S2 with the value VHDL. Okay, in Java there is an operator called plus, which is used to concatenate two strings like S1 plus S2. This operator has been overloaded in Java to perform concatenation operation. Clear? Now the result of this concatenation operation is you will receive a new string which will have the value hello followed by VHDL. This is called string concatenation. Exactly here in VHDL, this ampersand operator act like a concatenation operator. Clear? Now I am going to explain what is this part Q of 2 down to 1. Means after putting the bit present in the 0th place to the first place, what actually you are doing? What you are doing is you are extracting the bits starting from second place to the first place, and then you are appending these two bits. You are appending these two bits to the bit already placed in the first place, right? Exactly, you are doing the same thing here. So take the bit present in the 0th place, put it to the first place here, and then append this bit with the bits present from position 2 to position 1. I mean these bits 2 to 1, these bits. So again in the next cycle, or when you apply the clock, again the same process will happen. Means it will take the bit present in the 0th place, put it to the first place, then take the bits present in the place 2 to 1, then concatenate it to the bit with the bit already placed in the first place. So this is how it will work. Clear? Okay, now we're going to explain about Johnson counter, which is actually a modified version of ring counter. Again we shall assume here Again we shall assume here, let us assume that counter, we are dealing with an counter which has 3 flip-flops, and assume that initial value of the Johnson counter is 100. The decimal equivalent of this is 4. When you apply the clock, how this Johnson counter will work? So first it will take the bit present in the 0th place. Okay, first it will take the bit present in the 0th place, and then what it will do, it will concatenate it. I mean, using the NOT gate, it will concatenate it. Complement of this 0 is 1. Then it will place the bit present in this place to here, and this bit present in there to here. So the decimal equivalent of this will be 6. Means if the initial state of the Johnson counter is 4, when you apply the clock, it will enter into the state 6. Again, if you apply the clock, what will happen? Same. It will take the bit present in the 0th place, complement that. It will complement that. Complement of 0 is 1. Then it will put the bits present in this place to this place, and the bit present in this place to this place. The decimal equivalent of this is 7. Okay. So exactly in the same way the Johnson counter will work. So if you want to implement this idea in VHDL, so just first have a look at the port description. So we need a clock, we need a reset pin, and this is our counter called Q. The mode should be in and out. It should be a vector of dimension 0 to 2 because of 3 bits. And same, we have to use a process block. If you apply the reset, then counter should be stored with the value 100, which is nothing but 4. Then if you apply the clock, so this is important, only this part has been modified here when you compare to the ring counter. First you should get NOT of the bit present in the 0th place, and then concatenate with the bits presenting from position 2 to 1. So first you take this bit, I mean Q of 0, then complement it. Okay, you will get 1. Then you append that 1 with the bits presented from position 2 to 1. I mean these bits. Correct? So this is how the Johnson counter will work. Now we understood how actually the ring and Johnson counter will work, and how to write the VHDL code, right? So now we shall jump into the tool, and we shall try to implement ring counter first, and then we shall go to the Johnson counter. Clear? Okay, as usual you will get a tip. Okay, start with a new project and give the name as RC, which stands for ring counter. Okay, new source file, and the type of that file should be VHDL. Okay, then here clock, reset, then the counter, the mode should be in and out, and it should be 0 to 2, I mean dimension. Okay, clear. Next, finish, next, finish. Okay, automatically the code will be generated by the tool, which you already aware, and the construct that we need to use is process. Okay, then clock, then reset should be the parameters, and we should indicate the scope of the process with the begin keyword, and we should indicate the end of the scope of the process with the keyword end process, right? Okay, now what is the actual logic? First we should initialize the counter with a valid value, so that's why we have used reset, right? If reset is applied or reset is 1, okay, then what you have to do, then counter should have the value 100. Okay, since we are dealing with multiple bits, I am enclosing here with a double quotes. Clear? Okay, then else if you apply the clock, then what should be the value of the counter? Then counter value should be assigned with, first it should extract a bit present in the first place, Q of 0, and then it should concatenate with the bits presenting from 2 down to 2, down to is a keyword, down to 1. Clear? Okay, then end the scope of the if. So the logic is very simple. Clear? So I hope I have not done any mistake. If you have done a mistake, anyhow the compiler will identify that, then we shall rectify it. Go to implement design, synthesize, then ask for checking the syntax or check the syntax. Okay, once the checking of the syntax is comes with a successful status, then you can go ahead with the simulation part. So there is a mistake in approximately line number 40. Okay, line number 40. Okay, what is that mistake? Unexpected tick. Yeah, can you see here? Actually, there is a problem in line number 43. I have not ended the tick or a single quote, but actually it is showing the error in the line number 40. So be careful that actually the compiler will not give the actual number where actually it has an error. So at least you should look the above few statements and below few statements in order to rectify the problem. Then close this tick. Okay, close this tick. Okay, save this and ask for rerun. Okay, again there is a problem at line number 43. What is that problem? Parse error, unexpected tick at line number 43. Line number 43, unexpected tick. Okay, see here. Now actually there is an error in line number 46, but it is showing at line number 43. The same mistake we have done. We have not enclosed this within a single code. So like this, while learning, if you find an error, it will be useful so that we can learn how actually the compiler will behave. Now it has been compiled successfully. Now we shall go to the simulation part. As usual, go to project, new source, and the same waveform, test bench waveform. Define the waveform. Okay, fresh, and don't worry about this. Okay, and only one thing that you have to do here, it is set the reset high initially, then low. Okay, clock will be defined, it is predefined. Okay, now save this, select the waveform, go to process, and simulate, ask for simulate the behavioral model. Just you need to make reset high initially, then low, that's it. And why we have to do that initially? Simple, I have already said that in order to initialize the counter with the initial value that you have specified. See here. Okay, interesting. Since the reset is high here, the counter has a value 4, which is nothing but this 100. This is what we have instructed through the code, saying that when you see if reset is applied, then you set the counter to 4, right? So that's what it is doing here. And when you apply the clock, here you are applying the clock, When you apply the clock, if clock is 1, then you do this. So we already have learned theoretically that if the initial value of the ring counter is 100, I mean which is nothing but 4, when you apply the clock, it will go to the state 0, 1, 0. I hope you are getting how you get 0, 1, 0. Simple. Take this, put it to the first place, 1, 0, which is nothing but 2. That's what you are getting 2, right? 2. And after 2, if you apply the clock again, it is going to the state 1. Now we shall verify whether it is true. Again, if you apply the clock, it will go to 0 here, this 0 will come here, this 1 will come here. It will go to state 1, right? So like this, you need to justify whether what you are getting is correct or incorrect. Clear? So this completes your explanation for ring counter. Now with the same code, I am going to explain how to go ahead with the Johnson counter. All the steps will be same, and here this is the place where it will get changed. Not of this, I mean that bit should be done. That's it. Since I changed in the code part, I need to go back to the synthesis part, save the code, and again check for the syntax. Okay, now it has been compiled successfully. As usual, go to the simulation, go to the project, new source, you take a new waveform, or you can make use of the same old waveform, no problem. Okay, I'm taking the new waveform, okay, it should not have space, new waveform. Okay, next, finish, and click finish. Even here reset should be set to high initially, then to low. Okay, then save the waveform. This is our new waveform. Select it, go to process, go inside the simulator and ask for a simulate behavioral model. Okay, interesting. Again, even this counter, initially it has been set to value 4 because that's what you are doing here. If reset is applied, set the counter to 100, which is nothing but 4. If clock is been applied, then you do this. Now we shall see what it is doing. If the clock is applied from 4, it is going to state 6 here. How it is, we already have seen. Once again I am repeating here. If the initial value is 100, if you apply the clock, then the Johnson counter, what it will do, it will take this bit, complement this bit, complement of 0 is 1, then it will place it here, then it will shift this bit here, then it will shift bit to this here. So 100 decimal equivalent is 4. That's what you are getting here as an initial value. Okay, then if you apply the clock, it is going to the state 110. Decimal equivalent of this is 6. That's what you are getting. After 4, you are getting 6. Again, if you apply the clock, here you are applying the clock. It is moving from 6 to 7. How it is moving from 6 to 7? Again, apply the clock here. You take this bit, complement it, place it here. Then shift the bit present in this place, shift the bit present in this place. It will become 1, 1, 1, which is nothing but 7. So that's what here. So this is how we need to justify the Johnson counter to the examiner, and you should say that it is working fine. Clear? So with this, I will end the session. Finally, what we learned in this video is we learned 2 experiments. One is how to simulate and verify the working of ring counter, and how to simulate and verify the working of Johnson counter. Clear? So I will end this session. Okay, if you have any doubt regarding this, you can either send me a message or send me a mail or contact me even in person also, no problem. So thank you one and all.